So, hi. So we are part of the eBay team. I'll introduce uh, the product that we are building on. So this is something about me. I lead the research efforts at eBay on knowledge graphs at eBay NPD. NPD is a new product development group at eBay, which is focused on more cutting edge technology and also on the artificial intelligence side of eBay efforts. And yeah, I mean, no points for guessing that I love graphs. So let me start a bit on a bit about eBay. So we have around 160 million active buyers. This is the like 11 billion is the mobile volume we have. Uh, so yeah, so this is an interesting slide. So we have one point, like as you see, around more than a billion live listings, and like there's a misconception that eBay is all about like used items, but 81% of the items that are sold on eBay are actually new. So yeah, and as you see, we have like almost 13 million listings added through mobile every week. These are some fun stats about eBay. So every country, every site has their own priorities. In UK, there's like a makeup product sold every 3 seconds. So, and Australia has a wedding item purchase every 20 seconds. So every country has their own priorities, I guess. So yeah, let's talk a bit more about the product that I'm going to talk about today, eBay Shopbot. So Emil, thanks for introducing us in your keynote and to actually showcase that how we powered the eBay Shopbot, which is a chatbot through knowledge graphs. So a bit about Shopbot, right? What it is. So Shopbot is a personal shopping assistant. We built Shopbot as a shopping assistant inside the. To start with, we built it inside Facebook Messenger platform, but it supports multiple platforms now. So the way it is built, it can integrate with any chatbot platform. The need for Shopbot was basically to bridge the gap between regular search and natural language search. So on any search engine, if you today say that I want a gift for an 11-year-old who likes, say, Iron Man, right? Most of the search engines will fail. They'll like give you diapers because you said kid in it. They'll give you shoes of size 11 because you said 11 years in it. So it's a really hard problem to go from a natural language search engine or a regular search engine to a search engine which powers natural language. So this, yeah, so basically, as I said, like Shopbot supports natural language understanding. So let me back off a bit and really get into like what are we trying to solve here, right? So what is conversational commerce? Is basically a system where you interact with the agent as you would interact with a salesperson in a shop, right? So if you go to a shop to buy say sneakers, you'll say, hey, I'm looking for some shoes, and then maybe the salesperson will ask you like, okay, what are you going to use it for? And once you tell him what are you going to use for, then he might ask you what brand do you prefer, then maybe after that what color you prefer, and then probably what size of shoes you're going to wear, right? So this kind of multi-turn interactivity is really hard in a regular search engine. So when we built Shopbot, we started with building an AI platform which will support a dialogue system, similar to the one I just explained, like how you'll talk to a salesperson. So a key questions that we had when we built a system is how to really decide what is the next best question to be asked when a user is trying to search for an item on the platform, right? So there are a lot of bot frameworks like API.ai, with.ai, and bunch of them, but it's all based on like rule engines. So you have to encode a rule in it, and then it will start acting the way you have encoded the rule. So it's almost like a bunch of if then else, right? So, but if you can encode rules, but for a system like eBay, which has almost everything that's like under the roof that can be bought, like every object is there on eBay, right? So it's like 20,000 plus categories that we support for products, which have more than 150,000 attributes. So when I say attributes, it's like your brand, your color of the object, and any attribute about an object that you're trying to buy. So you really cannot take a rule engine to support this big, huge catalog that eBay has with more than 1 billion inventory and with like 20,000 plus categories to shop for. So we basically needed a solution which will scale, and we also needed a solution where how do you encode this inherent like human brain behavior, where when I talk to someone about shoes, the next thing he'll think about is like Nike or Adidas as a brand, and probably the second thing he'll think about is what are you going to use it for. But for a human, it's very like for us as humans, it's very easy to think about it in that form. Like it comes inherently with the knowledge that we have been building since childhood, I guess, right? And the stuff we are reading. So it all like bundles up for the decision making that we do daily. So yeah, so how did we then go about this, right? So we decided to try out a way which is not going to like just encode rules, but it should be more like a probabilistic inferencing problem, where given a particular intent that the user is looking for, you decide based on some probability like what is the next best question that you're going to ask. And how do you learn this probability? You look at like past eBay behavior. So like eBay has, as I said, it has like around 16 million like active buyers. So there is almost every product that's been searched has been searched, and every attribute that can be constrained has been constrained. So what we did was we went from the eBay's core user behavior data to form a probabilistic graph so that we can drive conversation on what questions to ask next. And this is where you'll see a graph database being used. So yeah, as I said, like almost everything that's being searched is already been searched on eBay. There is a nice paper by Peter Norvig which talks about how data is the key even in the deep learning or machine learning era, right? So you can have like amazing algorithms, but without data you almost cannot do much about it. And the biggest challenge we had was there are a lot of research and papers that are talking about how natural language generation can be driven through machine learning or deep learning, but none of them really have come out of academia and productionalized the actual conversation or dialogue system which are just based on deep learning. So we basically, and I'll go into more details on how the probabilistic graph underneath looks like. But what we ended up doing is we built an expert system based on a collaborative approach where you use past user behavior data and use that to the next users in a probabilistic way. So yeah, just peeling some of the layers out. So this is like the slide that you should pay attention in the whole talk. This and the one after that. So this is the natural language understanding system that we have built. So right now you can go to Facebook Messenger and try Shopbot and try queries like these. So what it will do is based on a query like this, which says like my husband needs some new black leather dress shoes, but I want to spend only $80 on it. Do you have anything? So what this does basically is cuts down the query into multiple components to do a deeper understanding of what the real user intent is. So you can see that we have detected the gender out of it, like what gender. So even if a female is searching for something, but you can search for your husband, or if a guy is searching for a wife, you cannot just use the personalized gender for the actual shopper. You have to look at what the gender is in the query. So in this case, a female is searching for her husband. So we've detected like the gender is male. And so the intent here is needs, which means it's a shopping intent. And then there is the item condition, which means you can buy, so on eBay you can buy used items as well as new. So she's clearly looking for a new item. And then the black leather dress shoes are really attributes of the product she's trying to look for. And there are some constraints like price, which we have to apply when we filter out the billion inventory we have. So this is a very cartoonish structure of what goes underneath. So if you're talking about shoes, we first determine like what gender is the user looking for. So if say it's women's shoes, then it will have different attributes that should be asked next compared to men. Maybe women care more about brand than men do. Men care about maybe color, which is going to be almost always brown most of the times. So based on those probabilities, we decide how to infer this and basically convert it into a Markov chain where you only need the current context to ask your next questions. So the NLU does the natural language understanding, and then we have a piece which does the e-commerce understanding, and this is what it looks like. So if you say something like, I'm looking for eggplant composites, right? I'm not a big sneaker fan, so I would have no clue what you're talking about. But because we have so much past user behavior data, there has to be someone who clicked on someone who's an expert in like say sneakers, who must have clicked on the right item. So you know from that item's attributes that when someone says eggplant composite, the attributes are like, it should be in the athletic shoes category, then the product brand is Nike, and they're mostly used for basketball shoes, what release date it was, and also the color is mostly purple and the material is composite. But there is a really nice and unique thing about this is that from this query, which is like a very common query, you determine from the graph that eggplant corresponds to purple. And the coolness about this is you can apply it in cases where you have not much past user behavior data. So if someone says like, I'm looking for an eggplant iPhone case, most of the times, I'm pretty sure he's not looking for eggplants on the case, right? So he is actually looking, or he or she is looking for usually a purple case. So from the previous one where we made the fact that Nike has tagged all these eggplant composites with the color purple, we associated or learned through our knowledge graph that eggplant is associated with purple, and now we can use it in a case where we absolutely don't know about what someone means when it says like eggplant iPhone case. So that's really cool, and that was totally possible only because of the probabilistic knowledge graph that we built. So this is an overview. Let me pause and go into an overview of how the system overall looks like. So when you so we have like a huge set of data, which is e-commerce data as well as world knowledge data, which comes from Wikipedia, Wikidata, and like bunch of other Freebase, DBpedia, bunch of data sources. So we combine this using the Apache Airflow scheduler to get the data into a knowledge graph form through Google Cloud and Spark Data Proc on Google Cloud, which is then eventually modeled as a graph and then pushed to Neo4j. So for us, technically, the graph is not just a database, which what most of the talks or most of the users of a graph database would do. So it's not BI for BI, or it's not for analytics either. For us, it's a store which is used as a cache for a machine learned knowledge graph. So for us, it's technically more than just a database. So once the data goes to the knowledge graph database system, we do graph inferencing on top of it to power query understanding, entity extraction, price prediction, determining trends, and the whole previous examples that I showed you how the inferencing works. And then once we have the data into the graph structure, we use a Dockerized system on top of Google Cloud Platform to deploy it. So most of the deployment structure and the service part, Anuj is going to go over that. So at a high level, this is what all we have in our current knowledge graph. We have around multi-billion nodes. Around, I think these are stats, a bit old stats. The relationships are now around like 20 billion. We have combined e-commerce data with Wikidata to power more of world knowledge, like when the product was released, what are the trends that people are following, because trends keep changing. So you have to be, you have to get world knowledge into your knowledge graph. And there are some machine learning aspects, which, as I mentioned, that we don't use the graph just as a database, but we use it as a probabilistic graphical model to store the graphical model and to use it as a cache during the runtime system. And then we have implemented some supervised models on top of it. So for example, if you are talking about, say, winter jackets, you don't want to get into just sport jackets. So because eBay has a winter jacket category, you want to actually make the categorization such that you have attributes from the winter jacket category. So those are the supervised models that are also living in the graph. Then there are some semi-supervised approaches where we use label propagation, which means that we have a whole curation team who actually curates the graph for trends. And what that means is, because we have like such a huge graph, they cannot sit down and like curate each of the nodes in the graph to mark the trends. So they'll mark like a subset of the graph with the trends, and we use label propagation to project it through the entire graph. One cool use case that we have recently served on Google Assistant, which you can try, is what's it worth. So what it basically does is you can say, I want to talk to eBay, and then you can either try to see an existing item that you have for how much price is going to be sold for, or you can check price for the latest products that are going to be launched. So you can say, what is iPhone 8 going to be worth, right? Or you can say that I have this old backpack that's lying around. It's this particular model, it's this particular color. What can I get for it? So that's also served through our knowledge graph. Yeah. So yeah, why Neo4j, right? So we have when we started, we did try some relational data sets, but we soon found out that more and more data sets that we add, the joins keep growing, right? So we are like, let's just forget about all these joins now. Let's try to dump everything in a graph so that any new data set you have, our pipelines go from anywhere from a week to 2 weeks to just add a new data set. So we never have to worry about joining ever again. And obviously Neo4j is battle tested. They have like good production support and stuff. But the tooling system is also pretty good. We could very easily do a lot of experimentation because of the interactive browser and the visualization that they have. And it's the only one that provides like graph algorithms on top of a graph database. Yeah, so I'll end with this before I hand over to Anuj. So, like as Emil also said, I think graphs are really the future for AI. So the way I see it is, I've had a lot of search experience before I joined the AI team at eBay. And what I've found there is almost every model that you need. So basically a search system usually needs an autocomplete system, a query recommendation system, a recommendation, item recommendation system. So all of that can be powered through a graph. So you can think of it as like your machine learning model cache, versus some other system can do your backend indexing. So all your business logic and the creative juices can live in the graph where you actually do the inferencing, and you can push only the part where you have to pull the items to the backend indexing store. Yeah, so I'll be available after for questions behind. So with that, I'm going to hand over to Anuj.
Thanks, Ajinkya. So, yeah, in this part of the talk, we'll focus on how we have evolved with Neo4j over the last year and a half, and also the key takeaways from this talk are how we containerized Neo4j database, and also how we deployed huge data models into Google Cloud using Kubernetes. So, yeah, before as a part of the new products team, we were prototyping a lot of stuff. So we got started, with a, oops, sorry. Yeah, with the new products development team, we got started prototyping a lot of stuff. And that's how we actually started using Neo4j, because we thought that Neo4j fits our case pretty much very well. And we were all one of the main aspects of this was also deploying to the cloud. So we used our tech stack was Docker. We used Kubernetes. And we had a polyglot service in the backend. Like we had some services written in Scala, some in Java, some used Go. So we wanted to make sure everything works out of the box. And yeah, so why did we decide Docker? So Docker gave us a very easy way to build, ship, and run applications through lightweight containers in the cloud. And we used Kubernetes because Kubernetes was the best orchestration layer out there, which would allow us to scale in, scale out our containers depending on what the traffic volume that we see out there. So yeah, so early days, it was, as I said, because we were prototyping, it was a huge monolithic Python service. And we had lots of different modules running in as a single Python, a huge Python code base. And one of them was the knowledge graph module. So here, so when you think of this from a container perspective, we had two processes. One was the whole Python service, and the other was the graph database. And initially, our models were pretty small. So, and one point was the graph database was actually a local host to the system. So yeah, so the problem with the huge Python service was as many of you might have encountered, we ran into the global interpreter lock issues. So that made us, we could only serve a couple of requests per second. So that means we were spawning more pods to serve more users. So we went back and we thought we should actually split all the services into individual microservices. And then, so what we started doing was, once the science team, that is Ajinkya and his team, they build the graph models, we used to bake the graph models as base Docker images. And we used to put them in the Google Cloud repository, which you can think of as a GitHub for Docker images. And yeah, and what we used to do is, in our service deployments, we used to have this Docker file refer to the base image, the current base image that was supposed to be deployed. And it used to pull the download the data and spawn the graph database. And then a Scala we wrote a Scala service on top of on top of the database to serve our APIs and all other use cases. So in this way, Graph was still a local host to the system, and we had two processes running. One was the Scala service, and other was the Graph database. So in a way, what this meant was we were limited in a couple of ways. First thing is, if our models grew huge, the deployment will become a bottleneck. So yeah, the deployment would have become a bottleneck. And the other was, pushing and downloading these models was taking a lot of time. So what we wanted to do was we wanted to have a solution that would work in all these cases. And in this version of the graph, we were still using Cypher queries. And we saw some latencies at the rate of a couple of seconds. And then we switched over to procedures, and we brought down our latencies to less than 100 milliseconds. Yeah, so like I said, so one of the Docker principles says you should never run multiple processes within a single container. And that is what we were doing. We were running a Scala service and also the Neo4j as a process within our container. And so that meant so we wanted to also get away from that. And the other thing was, whenever there was a pod restart, we used to go back and download the model and then restart the pod. So that would have also become a bottleneck. So yeah, and in the meantime, we had requirements coming up wherein the models were to the order of multi-terabytes, and also we were also thinking of launching in different locales. So the first versions of the Shopbot was only for US, but currently we also do it for the Australian data set. And some of the requirements, like I said, was minimal deployment time, and one of the main things was whenever we switch over from the old data set to the new data set, we wanted the switch to be pretty seamless. Like the end user shouldn't even know that we have switched over to a new data. Right? So that's how we arrived at the containerized solution. Even before I talk about containerizing, we thought like pretty much what we saw out there was a lot of folks used to spawn their own VMs and load balance their services to hit the VMs. We could have done that too, but that means we were taking away all the goodness from Kubernetes, and we're pushing all that load balancing and scaling up logic onto ourselves. So even though like it was a tried and tested model of spawning your own VMs, we went with containerizing the Neo4j DB. So most of the Kubernetes apps by default are stateless. That means they don't have any storage. And the way you provide storage for a Kubernetes app is through persistent volumes. And if you want to use a persistent volume and make sure your pod doesn't copy over the data always, there is something called as there was an alpha feature by Kubernetes, which is a stateful set. And stateful set ensures that, let's say, when you start a pod, it ensures that the data disk that is associated with this pod is constant in all the rollouts. That means we would copy the data only for the first time when we were doing the switch over for the data. And for some reason, if there was a pod restart or a hardware failure, on the consecutive next pod initialization, we wouldn't copy over the data. So that means we were avoiding multiple duplicate copies. So we'll go over I'll go over the deployment strategy that we followed in this slide. And so if you remember, we used to bake the models into the base Docker images. So instead of baking them into the Docker images, we started with using the Google persistent disks. So we used to bake the models into Google persistent disks, and during our deployment, that gets copied over to a local so so it gets copied over to the local PD, and this happens only for the first time. And then through a Kubernetes service definition, we could easily route the traffic from our Scala service to the pods. So in this example, we have 2 pods, and the Kubernetes service definition knows when the pods are coming up, and it routes the traffic. It load balances and routes the traffic to each of the pods. So let's say if our traffic increases, all we have to do is we have to change the deployment script to make sure we have, let's say we have 2 here. We change it to X number of pods, and Kubernetes takes care of scaling out. So yeah, so this shows the Scala serving service talking to the Neo4j US. So in a way, with this model, we one of the requirements, like I said, was also multiple locale data sets. So with this model, we were also able to work on getting the the Scala service to route on different Kubernetes service definition depending on the locale. So and each of these deployments are individual. And so for example, and let's say if there is a data change, like the science guys, they come up with the new data, and we again go through the whole process of creating a new original PD. And when we do the switchover, so one thing with stateful sets is it does a ordered termination of pods and ordered initialization of pods. So and that happens from in the descending order. So what it will do is it'll start from pod n or n minus 1, because the numbering is from 0 to n minus 1, and then it'll go on to the next pod whenever the next increasing pod is up and running. So that ensured, like, if there is any data corruption or something that we didn't catch in our tests or in the previous tests that the previous data sets that we have, one fallback was if the pod is not up because of any data corruption, we can stop that particular pod and stop the rollout, because stateful set ensures like the pod n to be up before working on the pod n minus 1. So we are still continuously evolving, and this was pretty new. And like I said, some of the things that we used were alpha features. We are still working with a couple of folks out there, and we're working on a few solutions on how we can be better. And as you can see, one of the limitations of this method is, for the first time, because it's a multi-terabyte model, your init phase takes a lot of time. Like it takes us a few hours to get one of the pods up because of the data copy. And yeah, and hopefully we can get to a stage wherein our deployment times are not in the magnitude of hours, but in a couple of minutes. So yeah, we'll be in the back for questions. So yeah.